So if I have the equation 3 to the x equals 9, I know intuitively that x has to equal 2 because 3 squared equals 9. Algebraically, I can find that by rewriting the 9 as a base of 3. So since 9 is 3 to the second power, now I have the same base of 3, so the exponents are equal to each other. And x equals 2 would be an algebraic way to show that solution. Okay, since a logarithm is an inverse of an exponential, which we learned when we were graphing, the log base 3 of 9 is asking this question, 3 to what power equals 9? And that answer is a 2. So the expression log base 3 of 9 is asking us this question to figure out what is the exponent, so that when I raise 3 to that power, the base of 3, I get an answer of 9. So the log base 2 of 8 is asking us this question, 2 to what power is equal to 8? And if I rewrite my 8 as a base of 2, 8 is 2 to the third power, so the x is equal to 3, which means log base 2 of 8 is 3. Okay. When you have a logarithm with no subscript, so the log of 1,000, that's called a common log, and there's an invisible or assumed base of 10 there for the common log. So log base 10 of 1,000 is asking 10 to what power equals 1,000. So if I rewrite this 1,000 with a base of 10, 10 to the third power is 1,000, and so my exponent is 3. So the common log of 1,000 is 3. Okay, out of these three log problems, only one of them can be evaluated in the calculator. Your calculator has a button right here for the log, but that button is a common log. So notice there's no place to put a subscript here, so the log of 1,000, when I press enter, that's asking what is the common log of 1,000, and the answer we get is 3. Okay, so go ahead and pause the video and try these three problems on your own, and then when you're ready you can resume the video and we'll go over them together. So the log base 7 of 49 is asking 7 to what power equals 49. And we know that 7 squared is 49. So if I rewrite that 49 with a base of 7, then x equals 2. So the log base 7 of 49 is 2. Okay, then we have the log base 5 of 1/5. So that's asking 5 to what power is equal to 1/5. And 1/5 is the reciprocal of 5, and that's a negative exponent. So 5 to what power equals 1/5 would be the same as 5 to the x power equals 5 to the negative 1. And now that my bases are the same, I set my exponents equal, and so log base 5 of 1/5 is equal to negative 1. Okay, the common log of 0.01, that's the same as the common log, which is a base of 10, of 1 over 100. Right, moving the decimal place over 2 places is 1/100th, or 1 over 100. So that would be asking 10 to what power is equal to 1 over 100, which is a 10 to the negative 2. And so now that our bases are equal, x is equal to negative 2. And the common log is the one that I could use my calculator, my TI-83, to evaluate. So if I did common log of 0.01, we can check that answer, and sure enough, we get negative 2. Okay, so on the front of your notes booklet for this lesson, evaluating logs, okay, this is the formula where you can rewrite an equation between exponential form and logarithmic form. So if y is equal to b to the x, right, we're asking in the logarithm, what is that exponent on the base? So the log base b of the argument y, that will give us the exponent that we're trying to find. Okay, a common log is a base 10 logarithm. It's assumed, but it's not written. And you also have a button on your calculator that says ln. Okay, that is the natural log. That's the same as a logarithm base e. And when you're looking at the calculator, okay, e, if we do second and then the division symbol, there's our e, you can get a decimal approximation for Euler's constant by pressing enter. So e is approximately 2.718281828, etc. E is a lot like pi. It's an irrational number, so it is a non-repeating, non-terminating decimal. It's a constant that has a lot of applications in business and science. A lot of natural phenomenon are based on this e constant, and since it's so common, we use the natural log for logarithms of base e, and that's this button right here. Okay, so let's try some problems together in example 1. So we're looking for the log base 7 of 343. And step 1 is to rewrite this log in exponential form using x as our variable. So we'll have a 7 to the x power equal to 343. Okay, then step 2 is to get a common base on both sides of the equation. And if you look at the table of perfect squares and higher powers that I gave you on the back of the notes booklet, we see here that 7 to the third power is 343. So I can rewrite this as 7 to the x is equal to 7 cubed. Okay, then step 3, set your exponents equal then to solve. So now our bases match. I know my exponents are equal, and x equals 3. So the log base 7 of 343 is equal to 3. Okay, example B, we have a common log because there's no subscript, so that's the same as a base 10. So 10 to the x equals, and then 3 decimal places over would be the 1000th place, which is a 10 to the negative 3. So now that my bases are equal, I set the exponents equal, and x equals negative 3. So the common log of 0.001 is negative 3. And since that's a common log, I can check that in the calculator. So we'll do common log of 0.001, press enter, and we get negative 3. Okay, example C, log base 1/3 of 729. So 1/3 is the reciprocal of 3, so we can write that as a 3 to the negative x power. And then 729 we can write as 3 to the 6th power if we look up in that table of values on the back of your notes booklet. So 3 to the negative x equals 3 to the 6th. And then we'll set our exponents equal, and negative x is equal to 6. And then when we divide both sides by negative 1, x equals negative 6. Okay, now there's no button on the calculator for the TI-83 that lets me evaluate a logarithm of a different base other than base 10 or base e, but I can work backwards to check my answer. So remember, we were asking what exponent do I need to put on 1/3 to equal 729. So now that I know that it's negative 6, I'm going to check that by putting in my fraction 1/3 and raising that to the negative 6 power. And sure enough, I get 729. So I can check my answer using that base raised to the answer and see if we get the argument of the log. Okay, so next we have the natural log of 1 over e to the 3rd power. Remember, a natural log is a base e, so we're asking ourselves e to the x equals, and then 1 over e to the 3rd, that's the reciprocal of e to the 3rd, which is a negative exponent, so that'll be e to the negative 3. Now that our bases match, we set the exponents equal, and x equals negative 3, so the natural log of 1 over e to the 3rd is negative 3. Natural logs we can evaluate in the calculator. So if I do the natural log, which is the ln button, of the quantity 1 divided by e raised to the 3rd power, and press enter, right, there we get our negative 3 as the answer, so we know that that worked. Okay, our next one, log base 27 of 1/9. So we want to take 27 to the x power and make that equal 1/9, which would be a 9 to the negative 1. And I want, in step 2, to get a common base on both sides of the equation. And when I look over at my table of values, 3 squared is 9, 3 cubed is 27. So I can rewrite both of these expressions with a base of 3. So 27 is 3 to the 3rd, and there's already an x in my exponent, so 3 to the 3x. 9 is 3 squared, and 2 times negative 1 makes that an exponent of negative 2. Now that my bases are equal, I can set my exponents equal, and 3x equals negative 2. Then I'll divide both sides by 3, and x is equal to negative 2/3. So that means the log base 27 of 1/9 is equal to negative 2/3. Okay, again, I can't check it in the calculator by using that base of 27, but I can check by using exponential form. So if I have my base 27 and I raise that to the power of my answer, negative 2/3, since a logarithm is an exponent, my exponent is negative 2/3 on that base. When I press enter, I should get the decimal equivalent of 1/9. And when I compare that 0.1 repeating to the decimal for 1/9, see how we get the same repeating decimal. So we know that negative 2/3 checks. Okay, next we're going to do the log base 16 of 8. So that's asking 16 to what power is equal to 8. And here we need to be careful. Students are tempted when they see 16 and 8 to think, oh, well, 8 is 16 times 2, so x must be 2. X is an exponent, right? We're not multiplying. So we need to change these to a common base and have this written as an exponent. Since 8 is 2 to the third power, I can rewrite 8 with a base of 2. When I look at the table, I can also rewrite 16 as a base of 2 with an exponent of 4. So the 16 to the x becomes 2 to the 4x. And now that my bases are equal, I can set my exponents equal. And, oops, 2 to the 4x. There we go. So then I'll have a 4x is equal to 3. Divide both sides by 4 to get the x by itself. And x is equal to 3/4. Okay, so the log base 16 of 8 then is equal to 3/4. And we can check that in the TI-83 by taking 16 and raising it to the 3/4 power, and we get back 8, so we know that that checks. Okay, so go ahead and pause the video, and I'd like you to try G, H, and I on your own, and then when you're ready to go over those together, you can resume and we'll check them. Okay, so we're back, and I asked you to do G, H, and I on your own so we could check those together. G is a common log of 10 to the 12th power, so the log base 10 to the x, right, or 10 to the x is equal to 10 to the 12th. You set your exponents equal, and your answer is 12. Okay, the log base 8 of 128 would be 8 to what power equals 128? When you look at the table up here, 2 to the 7th power is 128. So we rewrite this as 2 to the 3rd times x. So 2 to the 3x equals 2 to the 7th, which is 128. Set your exponents equal, and x equals 7/3. Then the log base 1/5. 1/5 is the reciprocal of 5. So that's a negative exponent, 5 to the negative 1. 1 over 3,125, we see up in the table that 5 to the 5th is 3,125, and since it's a reciprocal, we have a negative exponent. So 5 to the negative x equals 5 to the negative 5th, negative x equals negative 5, and x equals 5.